So now we will be starting with complex functions of linear algebra. So the definition of complex function is functions with complex variables. Complex function of complex variables. So w equals to f of z, where f of x plus iy equals to u of x comma y plus iv into x comma y. So an important function is the analytic function. Analytic function is a function if a complex function f of z is differentiable at a point z equals to z naught. That is, limit of z tends to z naught, as you have learned the definition of differentiation. F of z minus f of z naught by z minus z naught equals to f dash of z naught, and also it is differentiable in the neighborhood of the point z naught, which is a very important point. Then only fz is known as the analytic function. If a function fz is not defined or not differentiable at z naught, then z naught is called singular point of fz. So you can understand that a differentiable function, that analytic function is always differentiable, but a differentiable function is not always analytic. If a function fz is differentiable or analytic at every point within a finite complex plane, then fz is called as entire function. So this is the most important thing in the analytic equation. An analytic equation function must always satisfy the Cauchy-Riemann equations. So the necessary condition for a function fz to be analytic is if f of z equals to u of x comma y plus iv into x comma y is analytic at z naught, then u and v satisfy the Cauchy-Riemann equation. The Cauchy-Riemann equation states that ux equals to vy and vy equals to minus ux equals to vy and vx equals to minus uy at every point in some neighborhood of the point z naught, provided ux, uy, vx and vy exists. So the theorem 2 is the sufficient condition for the fz to be analytic is, that was the previous one was the necessary condition, and this is the sufficient condition. If fz equals to u of x comma y plus iv into x comma y is defined at every point in some neighborhood of the point z naught, then u and v satisfy the CR equations. Ux equals to vy and vx equals to minus uy at every point in some neighborhood of the point z naught. Here u, v, ux comma uy and vx comma vy are continuous at every point in some neighborhood of point z naught. Then the function fz is analytic at z naught and f dash z equals to ux plus ivx. So this is an example of a function. You have to check whether it's analytic or not. So use the Cauchy-Riemann equation, partially differentiate ux and vx, and uy and vy. So you here find that it satisfies the Cauchy-Riemann equation, ux equals to vy and vx equals to minus uy, and hence fz is an analytic function, and also it means that it is a differentiable function. So there is a second example. If u of x comma y equals to x square minus y minus 2 is a real part of the analytic function fz equals to u plus iv, then you need to find fz. So first you differentiate ux, u with respect to x, then you differentiate u with respect to y, and you know the Cauchy-Riemann equation. Since it's already given that it's an analytic function, then it satisfies the Cauchy-Riemann equation. You can find vx, and from theorem 2 you know f dash z equals to ux plus ivx. So you write it, replace x and z, x with z and y with 0. Then you find fz by differentiating the function with respect to z, and there's a constant come in c, where c equals to c1 plus ic2. There's a polar form of the variables r and theta. Delta u by delta r equals to 1 by r delta v by delta theta, that is ur equals to 1 by r into v theta. Again, delta u by delta theta equals to delta v by delta r, that is minus 1 by r into u of theta equals to vr, and f dash z equals to ur plus ivr into e to the power minus I theta. Next up you have the harmonic functions. So an analytic function is said to be harmonic if it satisfies the Laplace equation, which is uxs plus uyy equals to 0 and vxs plus vyy equals to 0. A function xy is called harmonic if ux, uy, uxx and uyy are continuous and the function satisfies the Laplace equation. So some points to be noted. If fz equals to u plus iv is analytic function, then u and v are harmonic functions. If u and v are harmonic functions, then f of z equals to u plus iv may or may not be an analytic function. harmonic conjugate function. If u and v are harmonic functions and u plus iv is analytic, then v is called the harmonic conjugate function of u. And how to find a harmonic conjugate? If v of xy is given, to find its harmonic conjugate u of xy, then du equals to delta u by delta x into dx plus delta u by delta y into dy. And du is delta u by delta x can be written as ux dx plus u by dy equals to vy dx minus vx dy. U equals to integration of vy dx between y constant plus integration of minus vx dy. Only consider the terms free from x. So here is an example. You need to find the harmonic conjugate. So you first write dv equals to vx dx plus vy dy equals to minus uy dx plus ux dy. You find ux and uy from the function given. Then you find dv by substituting the values of uy and ux. Then you integrate v with respect to x and x and y respectively, and then you find the function, and there is a constant k which is a real constant. So next I come with the Newton-Raphson method. So you can see there is a graph x of I plus 1 equals to xi minus fxi by f dash of xi. There is the derivation. You can just go through it if you want. So the algorithm for Newton-Raphson method is, you have to evaluate f dash x symbolically. You have to calculate the next estimate of the root and find the absolute relative approximate error by this formula. Find if the absolute relative approximate error is greater than the pre-specified relative error tolerance. If so, you have to go back to step 2 and else stop the algorithm. Also check if the number of iterations has exceeded the maximum number of iterations. So here is an example. You can do this sum if you want. The solution is provided here. You can go through it. This is the graph of the function which has been obtained in the previous. So this is the number 1 iteration, and you have find the error percentage. You have to calculate it with the actual function tolerance level. So the advantages of Newton-Raphson method is it converges fast if it converges and requires only one guess. There's the drawbacks of the Newton-Raphson method. The inflection point, you can get more than one number. Division by 0, root jumping, oscillations near local maxima or minima. So here I come to the end of the Newton-Raphson method. Now I would start with interpolation methods. So first let us consider an integral fx dx a to b, where fx be given certain equidistance value of x. Say x naught equals to a, x1 equals to a plus h, and xn dot 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 xn equals to a plus nh equals to b, and the entries corresponding to the arguments of y0, y1, y2, dot 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 yn respectively. Be a set of n plus 1 values of the function y equals to fx corresponding to the equidistant values x0, x1, x2, dot 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 xn of the independent variable x. That x0 equals to x0 plus nh, where h equals to xn minus x0 by h. It's basically the width of the bound, equals to b minus a by h, where a is the lower bound of the interval ab and b is the upper bound of the interval, and n is the number of intervals. So the limit change when x equals to x0, then u equals to 0, and when x equals to xn, then u equals to n. So this is the formula you have to use. This is the Newton's forward interpolation formula. Put in n equals to 1 in the equation above, you obtain the trapezoidal rule, you obtain the Simpson's 1/3 rule. Put in n equals to 3, you obtain the Simpson's 3/8 rule, and put in n equals to 6, you obtain the Wedel's rule. So what is interpolation and what is extrapolation? There are two types of interpolation we are going to study about: forward interpolation and backward interpolation. There's also a Lagrange's interpolation formula. So here is the Newton's forward difference formula. You have to use the formula which you just studied, and you have to solve the sum. The chart will be given, where u equals to x minus xn by h, and h equals to difference of x, which is always the equal interval. And this is the Newton's backward difference formula. It's the same, just you have to calculate from the back. So just try out this sum. I'm sure you can do it. So this is the Lagrange's interpolation formula. Given n plus 1 values of the function fx for x equals to x0, x1, dot 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 xn, normally f of x naught, f of x1, comma f of x2, dot 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 f of xn respectively. The formula states the fx is x minus x1 dot into x minus x2 into x minus xn by x naught minus x1 into x naught minus x2 dot 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 x naught minus xn into f of x naught plus dot 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 x minus x naught into x minus x1 into x minus x2 dot 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 x minus xn minus 1 by xn minus x naught into xn minus x1 into xn minus x2 dot 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 xn minus xn plus 1 into f of xn. There's an example, you can just try it out. The answer is also given. So these are the comparisons between Lagrange's and Newton's method. So you can easily find out which is the best. Lagrange's method is numerically unstable, whereas the Newton's method is numerically stable and more efficient. The Lagrange's formula is less better for computation, and the Newton's formula is much better for computation than the Lagrange's formula. And again, Lagrange's form is more efficient than the Newton's formula when we have to interpolate several data sets on the same data points, whereas Newton is less efficient for several data sets. With this, I come to an end of the course. Thank you.